Alright, I've been playing around with just linking all of the little pieces together, and I have just a demo set up here. Right now the high voltage DC pack is on, the 12-volt battery is connected, and what we're going to do is we're going to turn the key on to the car, which is this switch right here. And I've just got it now just kind of doing random things. So I just turned the key back off, and so all it can do right now is look for the grid charger being plugged in. It can also use the fans here, so it's spooling them up to full speed or not. I'm spoofing the temperature values obviously right now, and yeah, that's basically what it's capable of doing right now with the key off and the grid charger not connected. And of course, if we turn the key on now, then we can actually control the fan in the back, which you'll hear just turned on now. And we can still control the fans in the front. And then also we can control this grid charger. And right now the scheduler and the firmware is not running very quickly for this, so it can take up to about 10 seconds. What I'm going to do is I'm going to plug the grid charger in, and I'm also going to zoom back here just a little bit. You can see this is a programmable load, and I have it set to sync the current this guy provides. This is basically the lithium battery in charge mode. So what I'm going to do is I'm going to plug the grid charger in. So I've just plugged the grid charger in, and so that sends a sense pulse, which will eventually probably be an interrupt. Right now we're just pulling it. And when that happens, you're going to see the LED right here turn on. It'll happen in just a few seconds here. So we've just turned the grid charger on. You can verify that here because we're now charging the battery here. And then I am slowly ramping using the PWM signal here. I'm ramping that current down. So as I mentioned yesterday, we'll probably end up using a 350 milliamp charger, which is right about now. And but as you saw at the beginning, this did work at the 1 amp or whatever. I'm not using the larger supply. This is the supply I showed yesterday. It's a 1.4 amp charger. That is a 1.05 amp charger there. Regardless, we're going to be using a 350 milliamp charger, but you can see that many different chargers will work. But I think the default option will be the 350. So yeah, we're kind of just ramping through all of this data, but we're actually doing quite a bit of stuff right now. We're controlling the fans here, we're controlling the fan in the back, we're checking to see if the grid charger is plugged in. If it is plugged in, we're turning it on using this triac circuit, and then we are also PWMing its output power. So a lot of things going on the Mega right now. So that is, with that, we've kind of tested to death all of the analog components here, with the exception of the current sensor, which I'm going to come back to. I think the issue I was describing yesterday is that I didn't have the load turned on. So the way that I have the bipolar current sensor working in a unipolar mode, it actually sinks power into the 5-volt rail. If you don't consume that power in the 5-volt rail, then it actually causes the 5-volt rail voltage to creep up until there's a Zener diode that breaks down, blah, blah, blah. The way you prevent that from happening is you have to turn, I just actually have a programmable load that's 40 milliamps or whatever that we turn on when the current value gets high. I believe that's the reason why my upper end current values were starting to compress a little bit. So I'll test that. After that, I'll do the BAT-SI and MET-SI. Actually, the bug I found that I showed, I think in the video yesterday, I might not have, but basically if you drive the BAT-SI RS485 or the MET-SI RS485 lines, if you drive them into the MCM, it actually develops enough voltage for the MCM to kind of turn on, but it makes it do funky things. The most consistent funky thing that it does is it turns on the pre-charge hold. I'm sorry, no, it's the PDU fan low speed relay, which is one of the relays over here, and it turns it on even when the key is off. So that was a head scratcher last night. You could see all the diode drops across all the various things, and it's because the LT 1487, the RS485 MET-SI and BAT-SI pins were actually driving into the relay. So that was an interesting head scratcher. I'm really glad I made those enable select lines connected to the Mega, because BAT-SI is it's only receive and MET-SI is only a send. You know, you could be convinced that you could just tie the LTC part in either transmit or receive. The receive would be that side, the transmit would be that side. And the only reason that I connected those two pins on the Mega was so that I could reduce the power consumption. And it turns out here that it actually keeps us from leaving this relay on all the time. That would kill your battery. So what I'm going to do now is I'm going to turn the ignition back off. And you can see that even with the ignition off, as I showed yesterday, we're still monitoring for the grid charger. If the grid charger is connected, we're controlling its output current. It's about to reset right now. So there's our 1 amp. So yeah, it's working pretty well. And need to, once I finish the bat side, the MET side, and that current sensor issue, which I think I know the answer to, then we'll be able to put this in the car and see it work in the car. And assuming that all works out well, then I'll go ahead and solder all of the LTC 6804 parts on here. That's going to take a little while. As much as I want to pick and place it now, of course I've put all of the through-hole parts on, and the pick and place machine only has about 10 millimeters of clearance, so it would hit all of these things. So at this point I've forced myself to manually place all of those parts. Fortunately they're all the same, you know. All of these are 75 ohms, all of these are the same part, these are all 3.3K, and these are all 87, you know, whatever. So I'll just be able to place them very rapidly. But, you know, such is the life of prototyping. But it's all going real well. These constant current power supplies have a really weird current output as you PWM them. Unfortunately, the signals are completely asynchronous, so because I've isolated these electrically here, the PWM waveform versus the grid charger waveform are very, very different, but I can show you one of them, but I can't show you them both at the same time, basically, at least not on the same horizontal scale. So what I'm going to do is I'm going to turn on channel 3 here. This is a differential probe, so it's this probe right here, and I've got it sensing the current, so I've got it coming across this current sink here, and that way we can measure the voltage here. And what you'll see is that as we get closer to low current, so at full current, you'll see that this is running at about, let's see, let me make sure that I have all this set up. So we're on counter 3, channel 3, I don't need channel 2 here, but I do need to trigger off of channel 3 there, and yeah, there we go. So this is at the low end. So right now it's 200 milliamps, so we're running at about 15% duty cycle. You can see we're actually a square wave here, and now we've gone away completely. And when we come back, we're railing our ADC out there, you'll see that it's much faster. We're actually running, I think, up to 350 kilohertz on this supply. None of this is worrisome. We can definitely play around with it. Of course, you can see that it is working. But I just think it's interesting that the way that the current output on this supply works is not only adjusting the frequency, which is actually pretty common, but it's also adjusting from a sine wave output right here. This is full current, and about 25% duty cycle, it turns into a square wave. There's this weird transition region. I'm not 100% sure why they did that. I think it's because the power supply is going from a continuous conduction to a discontinuous conduction mode. I'm not going to look into it too much. You know, at the end of the day, we're using a smaller power supply, and so we're going to probably always be using it above that 25% duty cycle. But I think that it's, I guess my concern would be is that if you were doing like a compliance testing on this device, the power factor is going to be really low at lower duty cycles. I could measure that. I'm not going to. Again, I don't really care, but it's just something I observed here in my testing. And again, what I'll mention here is that at these lower frequencies, we're dropping down to like hundreds of hertz. Can't measure right now, but yeah, that's like, sorry, there's two different ranges I have to do on this. So in this first range, we are, 450 kilohertz there briefly. And then as we switch down, I've got to eventually raise this range. Or scope's getting railed there. So you can see we're down to 6 kilohertz now, and it gets worse. Yeah, it's pretty slow. I measured down to, actually I measured down to 4.6 kilohertz is the lowest value. So as always, technical and unnecessarily so. It's just something I observed. I think it's odd about the way this Thomas Research power supply works. But regardless, we're able to control it. It just has a slight nonlinearity and a slightly, actually probably considerably worse power factor at lower duty cycles. So yeah, that's that. So anyway, yeah, it's as I've mentioned several times, it's coming along quite well, and yeah, we'll hopefully get this in the car soon. I have no idea on the timeline. I usually never do, so it just kind of all happens when it happens. As always, thanks for watching. Another boring LiBCM bring up video.